In this video, we look at section 3.4, which is related to the chain rule. Okay, the chain rule is another shortcut. It's a shortcut for taking derivatives of very special functions. It's the shortcut for derivatives of a composition of functions. Okay. So, for example, let's start with looking at functions. Functions that are compositions. So let's just make sure we can recognize what a composition of functions is. Functions that are compositions. So, for example, if you have a function f of x, it could be e to the 2x. This is an example of a composition of functions, because there is a function f of z, which is the e to the z function. Okay? And then z could be equal to 2x. Okay? Notice that z is a function of x. And I've just chosen the letter z because that makes sense to me. And now what you're seeing is, since z is a function of x, we could probably write even g of x for z. Okay? So what I'm seeing here is I'm seeing e to the 2x is I'm seeing it as a composition of two functions, where those functions are f of z, the outer function. Let's call it the outer function. It's the function that is on the outside, f on the outside. And then g of x, this is called the inner function. The inner function, and it's the inner in the sense that it gets substituted into the z, where the z in the function f. Okay, so when I see something like f of g of x, that means that wherever I see the z in the function f, I then need to instead put in g of x wherever I see the z. And since g of x is 2x, that would be e to the 2x. Okay, so there's an example of a composition of functions. Okay, you may also see something like f of x is equal to x squared plus 1 to the 5th power. This is an easier one to see the composition of, in my experience, because most people are going to see f of z. They're going to see the 5, and it's on the outside. So you'll see this as z to the 5th power. And then you're going to see the inner function g of x is equal to x squared plus 1, because x squared plus 1 is on the inside of the 5. This one seems to make the most sense to people. So when we're seeing x squared plus 1 to the 5th, that is f of g of x. Okay, so we're seeing this as z to the 5th power, and wherever you saw the z, we were supposed to put g of x, but g of x was x squared plus 1. So we were seeing x squared plus 1 on the inside to the 5th power on the outside. Okay, so z to the 5th is your outer function, and x squared plus 1 is your inner function. Okay, so f of g of x, that's some letters that we could use for these functions. Notice also another example. Let's see how I could make this a little bit more difficult here. What if you have like f of x, let's try to use different letters here. H of x, so you have some function, the square root of x squared minus 5. This one also seems to be pretty easy, because x squared minus 5, you can see it inside or underneath the square root. And so it kind of makes sense that the outer function, the thing that is covering up the x squared minus 5, is the square root function. So f of z would be the square root of z, and I should probably call this h. Okay? And now you can let there be an inner function, let's call it q, q would be a function of x because the inner function is a function of x, so you would have x squared minus 5. And therefore, h of x is h of q of x, q of x being the inner function. So square root of z is the outer function, x squared minus 5 is the inner function. So there are 3 examples of compositions of functions, and I'll do one more to kind of return to what I think are the more challenging of the problems. How about q of x is equal to e to the square root of x. Okay. These are the ones that usually give the most trouble because, you know, it looks like what's on the outside is this square root of x. It looks like the farthest to the right, or it's hard to kind of understand the spatial relationships here. But the way you understand the inner and the outer is if you were going to do this on a calculator, and I asked you to find q of 1. Okay, what would you do? You do e. Let's not make that 1. Let's make that 5. Okay, you would put in 5 for x, so you would get e to the square root of 5. Now think about doing this on a calculator. The first thing that you're going to do is the inner function. The inner function is you first have to find the square root of 5. Okay? And then the second thing that you do, that's your outer function. Once you have the square root of 5, then you hit your exp button of that square root of 5. Since you did the exp second, that's the outer function. Okay? So that may help you kind of keep track of the outer and the inner. And therefore, we could say that q of z is equal to e to the z. And the inner function, we'll call it a of x. It's a function of x, is the square root of x. And therefore, when you put these two together, q of a of x is e to the a of x, but a of x was equal to the square root of x. Okay, so there's a quick review of compositions of functions, 3, 4 of them, and it's exactly these kind of functions that we need to talk about how to take the derivative of them. Okay, so let's move on to this step. Okay, well, let's move on to derivatives. Okay. So the chain rule equals the derivative, chain rule is the derivative of a composition of functions. Oh, I know, I misspelled that, sorry, functions. Okay, so let's take the function f of x. We take the derivative of functions. Okay, so you just get to make up a function, say x squared minus x to the 4th power. Okay, but this function is a composition. G of x is x squared minus x. F of z is equal to z to the 4th power. I have my outer function, outer and inner. Okay. So if you can identify an outer and an inner function, then the derivative of a function like this, f of x, is actually f of g of x. Okay. Here's how you do the answer with the chain rule. This is called the chain rule. So this triangle with a delta symbol over it is telling you how to do the chain rule. What you do is step 1. First, you take the derivative with respect to z of the function f of z. Take the derivative of the outer function. So you work out to n. The derivative of the outer function. Step 2, you evaluate, after you take that derivative, put in z is equal to g of x. So this is step 2. Substitute z with g of x, whatever your inside function is, your inner. And then the last step is to multiply by the derivative with respect to x of the inner function. So step 3 is to multiply by the derivative of the inner function. Okay, so let's see how this works in the example that we just made up right here. Okay, so our function f of x is equal to x squared minus x to the 4th power. But our outer function was f of z, was z to the 4th power. So the first step is to take the derivative with respect to the variable z of z to the 4th, which is just a power rule problem for z to the 3rd. Okay. The second step is to take 4z to the 3rd and evaluate wherever you see the z, you need to put in your inner function g of x. But your inner function was x squared minus x, which means that wherever you see the z, put x squared minus x, and that will be to the 3rd power. Okay, so those are the first 2 steps. And then you need to multiply. You need to bring in this multiplication symbol. And then you move on to your 3rd step, which is taking the derivative with respect to x of x squared minus x, which is just a power rule again, 2x minus 1. Okay? So the chain rule, the formula, tells you how to put all of these together. The derivative with respect to x of a function that's a composition. F of x was a composition. It was the derivative of f of g of x. The answer is going to be 4 x squared minus x cubed. That's the first 2 steps, then multiplied by 2x minus 1. So these right here was steps 1 through 2, and then this problem right here is part 3. Okay, and together, steps 1 through 3 give you the answer for the derivative of that composition. Okay, so there's one example of a chain rule derivative worked all the way out, and the 3 steps that I think are going to be helpful. Okay, let's try another example. Okay, page below. One more. Okay, so what we know, the chain rule says that the derivative with respect to x of f of g of x is equal to the derivative with respect to z, f of z, evaluated at z equal g of x, multiplied by the derivative with respect to x of g of x. This is the way I like to write it. Okay? Just preparing you that if you also like the book's method, what the book is going to write is f prime g of x multiplied by g prime of x. This says take the derivative of the outer function, substitute in g of x, then multiply by the derivative of the inner function. What we are saying is the same. Okay? So another example of using that formula would be if I ask you to compute the derivative with respect to x of e to the square root of x. Okay, what are you going to do? First of all, this is a composition of functions. This is some function f of x. Okay? But I'm hoping that you see that as f composed with g of x, where f of z is equal to e to the z, and I'm hoping that you see the inner function g of x is the square root of x. Okay. So what you're going to need is the derivative with respect to z of f of z, the derivative of the outer function. So that will be e to the z. You'll need g prime of x This is why I don't like the prime notation. We've got different letters going on here, so it's just the derivative with respect to whatever variable is there. Derivative square root of x is a power rule problem, otherwise known as 1 over 2 square root of x. So let's put all these steps together. The chain rule says that you're going to need the derivative with respect to z of the outer function, f of z. And that's step 1. And we know that that is e to the z. So you get e to the z for this step. Okay. Step 2, you need to evaluate at z is equal to g of x. Okay. So that's step 2. And then those two steps together, right, when you put step 1 and 2 together, you get e to the square root of x. Wherever you saw the z, put it in square root of x. Then the last step, you need to multiply by the derivative with respect to x of g of x, which is 1 over 2 square root of x. So if you put these three steps together, you'll get e to the square root of x multiplied by 1 over 2 square root of x. Also can be written as e to the square root of x divided by 2 square root of x. Okay. And there is the derivative of e to the square root of x. Okay. I'm going to advocate these steps because this will help keep you organized. Okay. So I'm going to throw in one more example. I would say this is a medium example. The first example was pretty easy. Okay, I'm going to throw in another example here, add page below. That may be a little bit trickier. This is a problem from the textbook. It's problem number 3, section 3.4, number 38, I believe. Okay. So here you're given a function h of z is b divided by a plus z squared to the 4th power. Okay, so z is our variable. The question is, do you see this? Oh, and the question says to please find h prime of z, or what they mean by that, the derivative with respect to z of h of z. Find that. Find this derivative of this function. And they'll probably say in the problem that a and b are constants. Okay. So the question you have to ask yourself before you start these derivative problems is, what rule are you going to use? Okay. Do you see this as something to the 4th power? Right? I do. I see this as q to the 4th power, where q is a function of z. It's b over a plus z squared. I'm going to split this into 2 parts. Okay, and therefore the derivative of h with respect to z is the derivative with respect to q of q to the 4th power. That's the derivative of your outer function. Okay, so h of z together is q, sorry, how do I write this? Sorry, equal to h of q of z. Okay, so this part right here is the derivative with respect to q, with respect to q of h of q, the outer function. Okay, then you're going to evaluate wherever you see the q, you're going to put in q as a function of z. Okay? And then you're going to multiply by the derivative with respect to z of q of z. That's the chain rule. Okay? So you have the derivative of your outer function was 4 times something to the 3rd power. But the inner function, once you do the substitution right here, wherever you saw the q, Q was equal to B divided by A plus Z squared. And then you need to multiply by the derivative with respect to Z of B over A plus Z squared. Okay. So I've successfully written down the chain rule. I just need to finish it by computing this derivative. But the derivative with respect to Z of B over A plus Z squared is going to require a quotient rule. Okay. So the quotient rule says that you have the lower function times the derivative of the upper function minus the upper function times the derivative of the lower function over the lower function squared. Okay? But the derivative of a constant is 0. The derivative of this is just going to be 2z. So the derivative of the inner function required a quotient rule. It's going to be minus 2bz over a plus z squared squared. So you're going to finish this problem off by writing the answer as 4 times the inner function, you left it alone, and then you multiplied by the derivative of the inner function, which was minus 2bz over a plus z squared squared. Okay? And, you know, for example, if they would like you to simplify, I know Wiley Plus is often asking you to simplify, remember that this is going to be the same thing as 4b cubed over a plus z squared cubed. That's the same. Multiplying by negative 2bz over a plus z squared squared. Okay, and multiplying fractions, you multiply across the top, so minus 8b to the 4th z divided by, and you have a plus z cubed multiplied by a plus z squared squared, and you get to add the exponents at that point to the 5th. So there's the derivative with respect to z of q of h of z. And that would be the answer I would put into Wiley Plus if they want it as a single fraction. Okay, so this has been a long video on some of the more handwritten problems of the chain rule. Later video we'll look at some more sneaky problems.